So let's take a look at the quantum description for this. What's our Schrodinger equation? Okay, we have a particle, we have a two-dimensional system here, right? So kinetic energy would be what? So it's going to be h hat psi equals E psi. Your Hamiltonian operator would be kinetic energy due to motion along the x-axis, so minus h bar squared over 2m, second derivative with respect to x, right? Plus motion along the y-axis. What's the kinetic energy operator for that one? Negative h bar squared over 2m, second derivative with respect to y. So that's your Hamiltonian operator, all right? I have it down here. And anytime you have this kind of symmetry in your problem, there's a circular symmetry in your problem, it's best to use, instead of Cartesian coordinates, to use polar coordinates. So if we did that, we can define our polar coordinates as r cosine phi, x equals r cosine phi, and y equals r sine phi. Well, how is that definition made? Well, let's see. If you have a circle right here, all right, and let's imagine a point here, xy, on your circle. And r is the distance from the origin, and you measure your phi from the x-axis. So angle phi is measured from the x-axis. Then you can see that x here is just equal to r cosine phi, right? And y is r sine phi. So instead of describing the location using x, y, you can use polar coordinates r. You can use r and phi. And the nice thing about making that transformation is because r is constant, this sum of this expression right here, you can show that that's going to be equal to negative h bar squared over 2mr squared times the second derivative with respect to phi. Okay, so it simplifies your problem a lot if you express your psi as a function of phi instead, as a function of angle. It doesn't depend on r anyway, because r is constant in this particular case. All right, now this term right here, mr squared, that's also known as the moment of inertia, so that's represented by I. Actually, going back to the earlier slide, I forgot to mention that. Oops, did I just... right here. This mr squared expression right here, that's what we call the moment of inertia. Okay. And notice the parallel in the similarity of this expression. P squared over 2m, that's equal to L squared over 2I. It's a good way to remember it. Okay. All right, so if you did that, like I said, your Hamiltonian is simplified. If you do a transformation of your coordinates from x and y to r and phi, you just have a Hamiltonian that depends on only one variable, phi, which makes it relatively easy to solve for the wave function. So how do we solve for the wave function? H psi equals E psi, right? So you say negative h bar squared over 2I, second derivative with respect to phi. I don't have to put partials anymore because it's really just one variable now. Psi equals E psi. Do we know how to solve this? We've seen this equation lots of times already, right?